Today's lesson is about the law of conservation of mechanical energy. Before we get started, let's review. I want you to name 3 different types of energy. You can stop the video and write them down. Okay, so some of the types of energy that we have talked about is thermal energy, electricity, nuclear energy, chemical energy, gravitational energy, mechanical energy. So that's just a few of the types of energy we've talked about. So today our learning target is I can explain the law of the conservation of mechanical energy. I have a video to show you, so please watch this video.
Okay, let's talk about the conservation of energy, where if energy is not gained or lost, where on earth did it go? So, law of conservation of energy states that energy cannot be created or destroyed, just changed to a different kind. And I've got a few examples right here where you can see this first one, ice cream, you eat it, and you're going to convert that chemical energy into the energy of motion. Sometimes the radiant energy from the sun can be converted into chemical energy through photosynthesis. Sometimes the chemical energy of gasoline can be converted into the kinetic energy of motion, or sometimes just straight up electrical energy from your outlets can be converted into thermal energy, like with a toaster. Light to chemical, electrical to heat, chemical to mechanical, more chemical to mechanical, although obviously don't switch the gasoline and the ice cream. But I want you to draw at least 2 of these in your notes, the conversion of one type of energy to a different type of energy. Pause right here, pick any 2 that you want, and draw them into your notes. All right, so examples of conservation of energy, by the way, it's in parentheses, so don't write this. The total energy in the system will remain the same, even when it's converted. So here I have someone throwing the ball up and down. So right here, it has the maximum kinetic energy. It is moving the fastest and the least potential energy because it's, lowest. As it gets to the top, the kinetic energy essentially zeroes out because it's not moving, but the potential energy is now at its maximum because it's highest above, most gravitational potential energy. And then as it goes down, it's going to be reconverted from potential back into kinetic. The total energy should remain the same. If you're biking up a hill, if you're coasting up, you get to the top, you have lots of potential but no kinetic, and you go down and all that potential turns into kinetic. The total amount of energy remains the same. This is, get it? Physics, not physics. If you've seen The Princess Bride, you get it. But potential energy being converted into kinetic, you should really see that movie. It's a classic. All right, so during this pole vault here, a guy is going up and over the bar. We have energy conversions. At the beginning, he starts by running. That type of energy is kinetic energy. Next up, that pole bends, and that's a type of potential energy. That's our elastic potential energy, which we were talking about before. Finally, the vaulter is raised to the highest point. That would be the gravitational potential energy. So he starts kinetic, elastic potential as it bends, and then it brings him all the way up to gravitational potential energy as he goes up and over the bar. Here you can see another example of that kinetic being converted to elastic, being converted into kinetic right in that face. All right, enough of that. Here's that same guy before that I've shown. Here you can see those energy conversions as they happen. I love how stubborn he is. But we start with kinetic, elastic potential, gravitational potential, elastic, and back to where we started with kinetic. All right. When you have the friction small enough, the total mechanical energy does not change. So the way we're going to write this, the kinetic and potential at the beginning is going to be the exact same as the kinetic and the potential at the end. So here we have a pendulum swinging back and forth. Here it has the maximum potential energy, but the least kinetic because it's not moving very far. Here, again, same as before, maximum potential energy, 0 kinetic. Down here at the middle, least amount of potential energy because it's at the bottom, but that's when it's moving the fastest. So here we have Neil deGrasse Tyson demonstrating the conservation of energy, and the energy that it starts with cannot possibly exceed the energy that it ends with, which is why he's not going to actually get hit by it. Here's another one here, a guy at MIT. It swings. He's confident it's not going to hit him. Oh, except it's Miley Cyrus. Never mind. Anyways, conservation of energy and friction. Friction will change kinetic energy into a different type of energy. Friction slows things down, and it converts movement into heat. If you've ever seen brake pads that get overheated because you're trying to slow a car down too much. So anytime you have machinery, friction reduces the efficiency. It's also a huge cause of energy consumption in cars and factories. So in a lot of cases, a lot of falling potential energy is converted to thermal energy. But the total amount does not change. You can't create energy, you can't destroy it. All that happens is it's going to be changed to a different type of energy.
Okay, so that video showed a really good example of how the energy is transferred from one source to another. And the whole idea of the conservation of mechanical energy is that energy is not gained or lost, it is only transferred. So one of the things that they talked about in the video was that the sum of the kinetic and potential energies of an object remained constant. Depending on where you are in your movement, depends on how much potential energy and kinetic energy there is. He talked about friction in the video, and in this slide, okay, this child has the most potential energy because he's at the very bottom. Gravitational energy has pulled him to the bottom. So as he's coming down the slide, the potential energy is just transferred to kinetic energy. If you look at this pendulum, the pendulum is all the way over to the right-hand side. Okay, you can see that this bar graph shows that the potential energy and the kinetic energy are the exact same thing. The speed and the height of the pendulum changes as it swings back and forth. So when it's down at its lowest, alrighty, the kinetic energy, that's the blue bar, is at the most. It has already come down. And then when it's starting to come up to the other side, the potential and the kinetic energy are almost the same. So if you look at this, if you add these two values together, remember we can get the values and we can put them together. It would be the same for each one of these pictures of the pendulum. All right, the potential energy is here. It swings down and stops. That would be the kinetic energy. And at the bottom of its swing has the most, the fastest speed. So then when it goes back up here onto this side, it's almost equal. The potential and the kinetic energy are almost the same. Okay, I want to show you this brain pop experiment, and I want to show you just exactly how this potential and kinetic energy changes, and this will help you with your Rube Goldberg assignment. All right. Okay, now when I start this skater, I want you to watch these potential and kinetic energy bars and the total. I want you to watch the total also. All right, so right now the guy's at the very top of the hill and it has the most kinetic energy. What do you think is going to happen down here? Okay, I want you to watch this for a couple of minutes. Well, just a couple of seconds. Okay. Oh, I'm trying to stop it where it's exactly the same, but I'm not going to get to. All right. So you can see how the kinetic and the potential energy changes as he goes up and down these hills. All right. And the total amount of energy stays the same. It doesn't change. This bar right here never changes. All right, let's watch it a couple more times. Okay, what if I make the guy smaller? What's going to happen? Look, the total amount of energy has been cut in half because I made him exactly half. Now, what's going to happen? Okay? It just goes a little bit faster, but the total energy is cut in half. What if I make it even smaller? Oh, look. There's not much energy there if I make this guy really small. Let's see what happens. All right. So, the mass, he's going the same speed, but the mass has changed. And the total amount of energy is smaller as the guy is getting smaller. When he gets bigger, there's more energy to be found. Okay? So what I wanted you to understand about this is to see how mass changes the energy and that the potential and kinetic energy stays the same. It doesn't, you're not gaining or losing any once you have made your different mass, your different object of mass, different mass. So, true or false? Exit ticket. Energy is always lost when work is done. True or false? Number 2, kinetic energy and potential energy added together is called what? Is that called mechanical energy? B, work energy? Or C, potential energy? All right, if you need help with these two questions, go back and watch the video or look at the slides that are posted in the iExcel classroom.